Good morning, students. Myself, Vijay Shankar from EC Department, Chevrolet Engineering College. Today, we are going to discuss about the examples in the Laplace transform. In the last class, we discussed the final value theorem and the remaining properties, and also some examples we started. That is A into sine omega naught t and A into cos omega naught t. In this class, we go for some more examples. That is Laplace transformation of e power minus at cos omega t and e power minus at sine omega t. The damped cosine wave is given as f of t is equal to e power minus at cos omega t. The damped cosine wave is given as f of t is equal to e power minus at cos omega t. Find out the Laplace transformation of this signal. So for the Euler's identity or Euler's theorem, cos omega t is e power j omega t plus e power minus j omega t by 2. And it is multiplied with the negative exponential e power minus at. And it is multiplied with the negative exponential e power minus at. So multiply this e power minus at with this cos omega t exponential values 1 by 2 into e power. For these two are bases are equal, we can add the powers here. Minus of a minus j omega into t plus e power, both are it is a minus, take the minus a plus j omega into t. But taking the Laplace transformation on both sides, the Laplace transformation of f of t and 1 by 2 into the Laplace transformation of the two exponential functions. What is the Laplace transformation of e power minus at? E power minus at is a 1 by s plus a. 1 by s plus a. Okay. 1 by s plus, what is the a here? A is a minus j omega. A minus j omega. You know the Laplace transformation. Remember here, the Laplace transformation of e power minus at is equal to 1 by s minus a. The a value, instead of a here, the a minus j omega. A minus j omega. So 1 by 2 into 1 by s plus the a here is a minus j omega plus for the second term 1 by s plus a is a plus j omega. For the second exponential value, the power, the coefficient of the t is a plus j omega. Simplify these two. 1 by s plus a minus j omega and 1 by s plus a plus j omega. Considered as x plus a is a and the j omega is a b, a minus b and a plus b, the a square minus b square, and a square is a s plus a whole square plus j omega whole square. It is a minus into minus again plus, and in the numerator s plus j omega and s plus a minus j omega. So minus j omega and plus j omega get cancelled. In the numerator, we'll get the 2 into s plus a. So 2 to get cancelled, s plus a by s plus a whole square plus omega square. Remember, my dear students, here. Now the Laplace transformation of e power minus at cos omega t is equal to, we got the s plus a by s plus a whole square plus omega square. So actually the Laplace transformation of cos omega t, what is the cos omega t? The Laplace transformation is s by s square plus omega square. So the Laplace transformation of cos omega t is a s by s square plus omega square. Now it is multiplied with the e power minus at. E power minus at. What is the e power minus at? The Laplace transformation is 1 by s plus e. 1 by s plus e. E power minus at. So the term s is changes as s plus e when the negative exponential is multiplied with the cos omega t. Understood, my dear students? The cos omega t, the individual, the Laplace transformation is s by s square plus omega square. Now, to find the Laplace transformation of e power minus at cos omega t, since the e power minus at, the Laplace transformation is 1 by s plus a. So wherever the s is there, you now change that is a s plus a by s plus a whole square plus omega square. Okay. Similarly, the Laplace transformation of sine omega t is omega by s square plus omega square. The last class we already discussed about the Laplace transformation of sine omega t. Now, what is the Laplace transformation of e power minus at sine omega t? Wherever the s is there, you can replace by the s plus b. So omega by s plus a whole square plus omega square. What it matters, friends? In a similar way, we already know. Now, what is the Laplace transformation of e power plus at cos omega t? E power plus at. What is the Laplace transformation of e power plus at? Plus at is a 1 by s minus a. 1 by s minus a. So wherever it is a s, we have in the Laplace transformation of cos omega t, I can keep the s minus a by s minus a whole square plus omega square. In the similar fashion, the Laplace transformation of e power plus at sine omega t is equal to, it is a s here in the Laplace transformation of sine omega t is a omega by s minus a whole square plus omega square. What it matters, students? If we know the Laplace transformation of e power minus at and the Laplace transformation of e power plus at, and after knowing that is the Laplace transformation of cos omega t sine omega t, to find the Laplace transformation of the product of the two functions, e power minus at cos omega t, e power minus at sine omega t, and e power plus at cos omega t, e power plus at sine omega t, wherever the s is there, you can change that s as s plus a when it is multiplied with e power minus at. Wherever the s is there, you can replace the s minus a when it is multiplied with the e power plus at. Got it, my students? These are all, it is a online bits only. But if you given the part A as your external examinations, 3 marks questions, these are what it matters, students. Now coming to the another example, determine the Laplace transform and ROC for the signal. ROC for the signal e power at mu of minus t. E power at mu of minus t. And this is e power minus e power at. The minus is also there. Total function is a minus, not in the power here. Minus e power plus at mu of minus t. I got the definition of the Laplace transformation. X of s is equal to integral minus infinite to infinite x of t e power minus s t dt. What it matters, friends? Now, in this example, you have to find out the Laplace transformation of the given signal x of t is equal to integral minus infinite to infinite minus e power at mu of minus t into e power minus st dt. Got it? So mu of minus t is a folded function of the step. Step function is varies from the 0 to infinite. Mu of t and mu of minus t is a folded function. So it is varies from the minus infinite to 0. Magnitude is the same for both the mu of t and mu of minus t, but it is a folded at the 0, mu of minus t. So now we can change the limitations from minus infinite to 0 by replacing the mu of minus t is a 1. So integral minus infinite to 0 minus e power at e power minus st d is equal to, now both the bases only, we can add the powers here. Minus is already there. Minus infinite to 0 e power, take the minus s minus a into t dt, that is equal to, what is the exponential integral here? E power minus of s minus a into t by minus of s minus a, because it is a coefficient of t. We are applying the integral with respect to the t only. Upper limit is a 0 and the lower limit is a minus infinite, and the total function having the minus. Got it? So this a minus and minus becomes a plus. Minus into minus is a plus. Upper limit is a 0 and lower limit is a infinite. Upper lower limit value e power infinite is a 0 and upper limit e power 0 is a 1. So 1 by s minus a. So this is for exponential positive. The Laplace transformation, that is equal to 1 by s minus a. Got it, students? So for positive exponential value, 1 by s minus a. Now only we see, and negative exponential value is a s plus a. But what is the ROC here? The ROC is very important. The region of convergence, whenever it is multiplied with the mu of minus t. Mu of minus t. So mu of t also will get the same thing. Mu of t is also will get in the same thing without any minus here. E power at mu of t, you can find the Laplace transformation. We will get the 1 by s minus a only. But here the mu of minus t, the ROC is s minus a. S minus a is because it is the minus 0 to the infinite, it's a less than value. Okay. See, we got x of s is equal to 1 by s minus a, and s minus a is a less than the 0. Why it is a less than the 0? Because the t tends to the minus infinite to 0. We are taking the limitations is from the negative real axis. So negative real axis, s is less than a. S than a towards the negative real axis. Totally this is a shaded area what we have here, less than the a. The ROC, the region of convergence. If s is greater than a means in the positive real axis. So minus infinite to the value up to the positive plus a, all the values is existed for the function what we are taking, the e power at mu of minus t minus value. Got it? Minus e power at mu of minus t, the Laplace transformation is 1 by s minus a, and its opposite is s is less than a. Why we are taking the S is less than A? Because of applying the limitations here. We are taking the integral limitation minus infinity to 0. So it is a less than the plus A. Got it, my dear friends? The Laplace transform will coverage if S is less than A. For S is greater than A, the integration will be the unbounded. When it is a bounded, when we take the values is S is less than A, it is a shaded area towards the negative real axis. If any value you can take below the values of plus A, it is a bounded. You can take any values of greater than the A values, it is unbounded. S is greater than A, the integration will be unbounded. Okay, you can call it as it exists for all the values of S from minus infinity to plus A, the Laplace transformation exists. Otherwise, it is not exist. Nothing but is bounded and the unbounded values. Remember, for e power plus t mu of minus t. What is the ROC? The difference here, if I explain x of s, and now I'm taking the x of t is equal to e power at mu of t. E power at mu of t. X of s is equal to integral minus infinity infinite x of t e power minus st dt. Okay, I'm taking here now is a mu of t. The limitations now stored here, the e power minus integral minus infinity infinite x of t is e power at mu of t into e power minus st dt. Mu of t is equal to 1 in the ranges of 0 to infinite. So e power at e power minus st dt. Got it? Now the basis of the same, you can add the power e power minus, you can take s plus or the s plus s minus a into t. Now it is e power minus st and e power plus at. And integral 0 to infinite. With respect to the t, we are applying the integral for the exponential. Okay. So what is the integration for exponential e power minus x of minus a into t by minus s minus a. Now upper limit is infinite and lower limit is 0. When you substitute the upper limit, it becomes of 0 minus, and lower limit you can substitute as a t, e power 0 is a 1 by, and in the denominator we have the minus of s minus a. Minus of s minus a. Minus and minus get cancelled, is a value is 1 by s minus a. When we can take the Laplace transformation of e power at mu of t, the value is the same for s minus a. Even the Laplace transformation minus e power at mu of minus t. But this Laplace transformation is also the same, s minus e. Minus e. But what is the difference? ROC is the difference. What is the ROC for this one? ROC is greater than. Why you are taking the greater than? It is a t values is varies from 0 to infinite. The ROC is greater than a. The region of convergence greater than a. The graphical representation is the totally the above values. The Laplace transformation exists. S values is greater than the a. And coming to this one, the ROC is S is less than e, and the Laplace transformation is bounded for the values of S is less than e, in between of minus infinity to a values. Okay, for this reason, we have to See what is the ROC of the given function in the time domain functions. With ROC only you can find out the inverse Laplace transformation. So if it is S is greater than A, the inverse Laplace transformation of 1 by S minus A is e power at mu of t. And 1 by S minus A, what is the inverse Laplace transformation is e power minus e power at mu of minus t. When the ROC is S is less than A. Without knowing this ROC, S is greater than A and S is less than A, it is somewhat difficult to write the inverse Laplace transformation, for which value it is 1 by S minus A, and here also 1 by S minus A. And what is the inverse Laplace transformation? That is the e power at mu of t or minus e power at mu of minus t. We don't know. With this ROC only, we can justify that for 1 by S minus A, what is the inverse Laplace transformation? For which values of S the Laplace transformation exists, that is depends upon the ROC only, the region of convergence. Got it, my dear students? Okay. So coming to the next one, the relation between Fourier transform and the Laplace transformation. Relation between Fourier transform and the Laplace transformation. We know the Fourier transformation is given as x of omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt. The Fourier transformation can be calculated only if x of t is absolutely integrable. This is one of the ROC of the Laplace, not the Laplace, Fourier transformation. We can call it as a discrete conditions. That is the first one. It is absolutely integrable. Finite discontinuities, finite maxima and minima, and single valued property, and absolutely integrable. These are all it is the conditions, the necessary and sufficient conditions for the Fourier transformations and the Fourier series also. Discrete conditions we are calling it as. So in that, the one of the condition is absolutely integrable, integral minus infinite to infinite, the magnitude of x of t dt is less than infinite. We know that S is equal to sigma plus j omega, where sigma is a real term and the j omega is an imaginary term. We can substitute in the definition of the Laplace transformation, x of S is equal to minus infinite to infinite x of t e power minus st dt. On the definition of Laplace transformation, x of S is equal to minus infinite to infinite x of t e power minus s into t dt. What is the S here? Sigma plus j omega. Integral minus infinite to infinite x of t e power minus of sigma plus j omega into t dt. Got it? That is equal to integral minus infinite to infinite x of t, expand these two or split the two parts as e power minus sigma into t as of one function and e power minus j omega t dt. You can see these two equations. X of j omega is equal to integral minus infinite to infinite. Instead of x of t, here it is multiplied with the e power minus sigma into t. E power minus j omega t and e power j dt is the same. Okay, so comparing the above equation with the 2.6, we find the Laplace transformation of x of t is basically the Fourier transformation of the signal x of t e power minus sigma t. The Laplace transformation of x of t is basically the Fourier transformation of x of t e power minus sigma into t. If x is equal to j omega, you see it. If x is equal to j omega, that is sigma is equal to 0 in the above equation. S is equal to j omega means sigma is equal to 0 because here the S is equal to sigma plus j omega. Integral minus infinite to infinite x of t, sigma is equal to 0 means e power 0 is a 1. E power minus j omega t dt. So you can replace S as x of j omega and sigma is equal to 0 here. At sigma is equal to 0. Now both the equations are the same. X of j omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt. So x of s is equal to x of j omega. X of s is equal to x of j omega. X of s is a Laplace transformation and x of j omega is a Fourier transformation. This means the Laplace transform is same as the Fourier transform. Same as the Fourier transform when s is equal to j omega. The above equation shows the Fourier transform is a special case of a Laplace transform. Thus, the Laplace transform provides a bordered characterization compared to the Fourier transformation. S is equal to j omega indicates imaginary axis in complex explain. Thus, the Laplace transform is basically a Fourier transform on imaginary axis in the S-plane. Got it, my dear students? What is the conclusion here? The relation between the Fourier transformation and the Laplace transformation is the Laplace transformation is basically a Fourier transform on imaginary j omega axis in the S-plane. On imaginary j omega axis in S-plane. Okay. Convergence of Laplace transformation. What is a convergence here? Previously, we are saying there is a convergence in the Fourier transformation is one of the discrete condition, absolutely integrable. Now, because of the relation is there with the Laplace and the Fourier transformation, the Laplace transformation is also convergent. For the signal x of t e power sigma t, the dt is less than the infinite. For the equation, we know the Laplace transformation is basically the Fourier transformation of x of t e power minus at. Hence, if Fourier transform of x of t e power minus sigma t exists, then the Laplace transform of x of t is exist. For Fourier transform to exist, x of t e power minus sigma t must be absolutely integrable. Must be absolutely integrable. Got it, my dear? Simply, we can say that is s is equal to j omega. The Fourier transform, Laplace transformation becomes to the Fourier transformation, or otherwise, the signal x of t e power minus sigma t. That sigma is a real axis. Is a Fourier transformation of Laplace transformation of the signal x of t e power minus sigma t. Or the Laplace transform is basically a Fourier transformation on the imaginary axis in the S-plane. Since the sigma is a 0 there, a point on the imaginary means a real term is a 0. A point on the real means imaginary axis is a 0. Got it, my dear students? Okay. Now, another examples you can see. We already seen the calculate the Laplace transform and ROC of e power minus at mu of t 1 by s plus a, and ROC is s is greater than minus e. S is greater than the minus e here. The shaded area is a minus e, and in the similar fashion is a positive and the negative, and we have already the properties we discussed. See, one of the property we are not discussed is a time scale. So ninth one is missed there. After the 8th, we go on for the 10th one. And another two properties are not we discussed here. The time scaling, if Laplace transformation of x of t is x of s, then the Laplace transformation of x of at 1 by a, the magnitude of a, and the x of s by a. So we got the definition of the Laplace transformation. I'll explain here. So one of the property what we missed in the earlier, that is a 9th property. The Laplace transformation of x of at, scaling property. We call it a scaling property, is equal to 1 by the magnitude of a and x of s by a. Okay, what is a scaling property? And this property is also we already discussed in the Fourier transformation also. Fourier series proof, not the solution, it is proof. You got the definition of a Laplace transformation. X of s is equal to integral minus infinite to infinite x of t e power minus st dt. We need to find the Laplace transformation of x of at is integral minus infinite to infinite. Substitute that x signal, the time domain signal, x of at e power minus st dt is equal to, now assume at is equal to some m and t is equal to m by a, and apply the derivative with respect to on both sides. So dt is equal to 1 by a into dm. Now you can replace here minus infinite to infinite x of at x of at is equal to m e power minus s, t is equal to, now it is m by a into dt, dt is a 1 by a into dm. Okay, now write the 1 by a in outside, 1 by a. Now it is in the form of integral minus infinite to infinite x of m e power minus s by a whole multiplied with m into dm. Now observe here the definition of the Laplace transformation, and here the x of m and e power minus s into m and dm. Instead of s, it is s by a, and the t is with the dummy variable of m. Now, if it is a e power minus st, the Laplace transformation is x of s. Instead of s, it is s by a. It becomes of 1 by a x of s by a. You can take it as a magnitude s of a. So the scaling property saying the Laplace transformation of x of t is equal to, x of at is equal to 1 by a, the x of s by a. Got it, my dear students? Now, that is one of the property we missed in the previous. Already discussed the linearity property, time differentiation property, time integration property, frequency shift property, time shift property, frequency differentiation property, and frequency integration property, and the other one is a time scale. Okay. Periodicity property also. Periodicity property. About the periodicity property, if x of t is equal to x of t plus n into t as a continuous time function, n is any variable, x of t plus n into t. Periodic with the period of t, it is a repeated the intervals. And x1 of t is a one period of x of t. And the Laplace transformation of x1 of t is x1 of t e power minus st dt. And in the range of 0 to t only, because it is a periodic product. Within this period only, the value is repeated. Then the Laplace transformation of x of t plus n into t, when the t changes with the n plus t is added, it becomes of 1 by 1 minus e power minus st, and the same function, integral 0 to t x1 of t e power minus st dt, nothing but x of s or x1 of s. Got it, my dear students? Okay. Now, using that it is a Laplace transformation of x of t plus n into t is 0 to infinite x of t plus n into t e power minus st dt, and it is varies only the repeated functions from 0 to t e power minus st when n is equal to 0, and n is equal to 1, it is varies from the t to t because it is a repeated again, and n is equal to 2, it is changes from the 2 to 3t, 2t through 3t. Is for every t variables, the n is changes. This goes on added for the 2t, 3t, and 3t, 4t, and so on. The value, the last function is n into t, n plus 1 into t. Or we can take it as a p minus 1 into t, or n minus 1 into t is n t up to the value of, and so on the infinite, because of the, we can take it as a repeated up to the infinite. Periodicity means always it is a repeated at regular intervals of 0 to t, t to 2t, 2t to 3t, and so on. And this, all the sum of values you can write as sum of p is equal to 0 to infinite. P is equal to 0 to infinite. P into t up to so on p plus n into t, because it is increases up to the t value. So p is a one term and the p plus 1 into t. 2 plus 2, t plus 2, and 2t to 3t is one value increases in the upper limit. So p into t, p plus 1 into t, x1, the t minus, it is a minus, why I have the minus, it is not the minus, my dear students, it's a plus only. T plus in p into t, e power minus s into t plus p into t. Okay, the t values changes as t plus p into t and the t plus p into t dt. Don't put here the t plus p into t because it is a variable. Got it? The sum of p is equal to 0 to infinite, integral 0 to t, x1 of t e power minus st and e power minus p into s into dt. Why I am replacing this x of t plus pt is x1 of t? The condition is given here. The condition is given, it is a periodic signal. Okay, it is not the pt plus, my dear students, is a plus. So x1 of t, because x of t is equal to x of t plus n into t. Now the variable is a p here, 1 and 1. So x1 of t is equal to x1 of t plus p into t. Okay, so I replace x1 of t plus pt as a x1 of t, because it is a periodicity obeys e power minus st and e power minus ps into t. That is equal to integral 0 to t x1 of t e power minus st, and we have only the p in this expression. Sum of p is equal to 0 to infinite e power minus p st into dt. Got it, my dear students? And integral 0 to t x1 of t e power minus st dt you can write as one function, and the sum of p is equal to 0 to infinite e power minus p st. Now expand this function as e power p is equal to 0 means 0 minus plus e power p is a 1 now, 1 into st plus e power minus 2 into st plus e power minus 3 into st and so on. It is nothing but you can assume it is a value e power minus power 0 and e power minus st and another one is e power minus t whole square and so on. So a power 0, a power 1 and a power 2 and so on means 1 by 1 minus a. 1 by 1 minus a. What is the a here? E power minus st. E power minus st. I already told that is a sum of n is equal to n1 to n2. A power n is equal to. So the a power n means e power st whole power p value. This value is a power n1 minus a power n2 plus 1 whole divided by 1 minus a, and a is always less than 1 and n2 is greater than the n1. This is a formula here. What is the value of n1? 0. So substitute the a as a power 0 minus what is the n2 infinite? A power infinite plus 1 and whole divided by 1 minus a. That becomes of a power 0 is a 1 and a power infinite is a 0 and 1 by minus a is equal to 1 by 1 minus a. Is the same thing. Here it is a value is e power st is equal to that of sum of p is equal to 0 to infinite e power st whole power p value. So n is equal to n1 to n2 a power n and p is equal to 0 to infinite a power p1. So it is multiplied with 1 by 1 minus e power minus st and this function. So for a periodicity property saying that 1 by 1 minus e power minus st is a capital letter, my students, not the small letter here, st multiplied with the integral 0 to t, nothing but x1 of s, the Laplace transformation. Got it? So periodicity property. The total function we can conclude it as x1 of s, and this also x1 of s1. Got it? That is one of the other property we missed in the previous